13.6 billion light-years away, in a galaxy that existed when the universe was only 330 million years old, something is shining that, according to every model of the early universe we currently have, should not be visible at all. Not fainter than expected, not slightly off. Completely, physically blocked, the way a flashlight beam gets blocked by a solid wall. And yet the James Webb Space Telescope caught it anyway, clear and unmistakable, coming from one of the most distant objects ever observed. Scientists published the finding, checked it, and are still not entirely sure how it's possible. Stick around because I'm about to walk you through exactly what this signal is, why it breaks the rules of early cosmic history, and what it might mean for how the very first galaxies actually formed. And if you want more real space discoveries broken down without the exaggeration, hit subscribe now, because this is final proof, and this one genuinely has astronomers stuck. To understand why this signal is such a problem, you first need to understand what the early universe was actually like, because it wasn't the calm, twinkling star field you'd picture from a planetarium show. It was closer to being trapped inside a thick, opaque fog. For roughly the first several 100,000 years after the Big Bang, the universe was too hot for atoms to even exist in a stable form. Electrons and protons zipped around separately in a dense plasma, and light couldn't travel freely through it because it kept scattering off all those loose charged particles. Then, as the universe expanded and cooled, something changed. Electrons and protons finally combined into neutral hydrogen atoms, and light was set free to travel in straight lines for the first time. That moment left behind the oldest light we can still detect today, the cosmic microwave background, the faint afterglow of the Big Bang itself. But here's the part most people don't know. Right after that moment, the universe didn't light up, it went dark. There were no stars yet, no galaxies. Just a vast, cooling sea of neutral hydrogen gas, stretching in every direction, completely opaque to a very specific and very important kind of light. Astronomers call this stretch of cosmic history the Dark Ages, and it lasted for tens of millions of years, until gravity finally pulled enough of that hydrogen gas together to ignite the first stars. Once those first stars and galaxies switched on, they started pumping out intense ultraviolet radiation, and that radiation began doing something remarkable. It started ripping electrons back off the neutral hydrogen atoms filling the universe, a process called ionization. Bubble by bubble, region by region, this radiation slowly burned away the fog, in a process astronomers call the era of reionization. It wasn't instant. Models and observations both suggest this process took a long time to finish, roughly 1 billion years after the Big Bang, before the universe was finally fully transparent the way it is today. Here's why that timeline matters so much for this story. There is a specific, extremely bright kind of light given off by hydrogen atoms called Lyman-alpha emission. It's one of the most useful tools astronomers have for studying distant galaxies, because it's so bright it can be picked out even at extreme distances. But Lyman-alpha light has a very specific problem. It sits at almost exactly the wavelength that neutral hydrogen gas is best at absorbing. Which means, during the Dark Ages and through most of the reionization era, any Lyman-alpha light produced by an early galaxy should have been swallowed almost immediately by the surrounding fog of neutral hydrogen still filling the universe around it. Based on decades of theoretical work and prior observations, astronomers were confident that this particular kind of light simply could not survive the trip to us from anywhere earlier than about 550 million years after the Big Bang. Before that point, the fog was supposed to be too thick. Case closed, as far as the models were concerned. That's the rule the James Webb Space Telescope just broke. If you're the kind of person who wants space explained clearly instead of buried under jargon, go ahead and drop a like right now. It genuinely helps this video reach more people who'd enjoy it. The galaxy at the center of this is called JADES-GS-Z13-1, discovered as part of the JADE survey, the JWST Advanced Deep Extragalactic Survey, led by a team that includes Daniel Eisenstein at the Harvard-Smithsonian Center for Astrophysics. Using Webb's NIRCam instrument, researchers first identified the galaxy as an extraordinarily distant object, and follow-up spectroscopy nailed down its redshift with precision. Redshift is essentially a measurement of how much a galaxy's light has been stretched by the expansion of the universe on its way to us, and the higher the number, the farther back in time you're looking. This galaxy came in at a redshift of 13, placing it at just 330 million years after the Big Bang, a little over 2% of the universe's entire current age. That alone would have made it a genuinely significant discovery, but then researchers led by Joris Wittstock, along with Roberto Maialino from the University of Cambridge and University College London, took a closer look at its spectrum, the detailed breakdown of exactly which wavelengths of light the galaxy was emitting. And there it was. A sharp, unmistakable spike of Lyman-alpha emission, sitting right where physics said it had no business appearing, more than 200 million years earlier than any previous confirmed detection of this kind of light. Maialino described the problem directly. The early universe, in his words, was bathed in a thick fog of neutral hydrogen, and that fog was only lifted through the long process of reionization, a process not expected to have finished until roughly a billion years after the Big Bang. This galaxy is seen at just 330 million years, and yet it's showing exactly the kind of clean, telltale Lyman-alpha signature that should only be visible once that surrounding fog has fully cleared. The result, in his own assessment, was totally unexpected by every existing theory of early galaxy formation, and it caught the entire research community off guard. The findings were published in the journal Nature. Here's what makes this more than just an academic curiosity. This isn't a faint smudge that might be a measurement error, or a signal buried in noise that needs a decade of confirmation. It's a sharp, clean, unambiguous spectral spike, captured by one of the most precise instruments ever built. The measurement itself isn't really in question. What's in question is how something like it could possibly exist at that point in cosmic history, given everything we thought we understood about how thick that early hydrogen fog actually was, and how long it took to clear. So researchers are left working through the possible explanations, and each one, if confirmed, would mean rewriting a piece of how we think the early universe actually developed. The first possibility is that this galaxy is doing something unusually aggressive to its own surroundings. If the young stars inside it are unusually hot and unusually metal-poor, meaning built almost entirely out of the simplest elements left over from the Big Bang, rather than the heavier elements that later generations of stars would produce, they could be putting out an extreme amount of ionizing ultraviolet radiation. Enough, potentially, to burn a large, clear bubble through the neutral hydrogen fog immediately surrounding the galaxy itself, carving out a private clearing in the cosmic haze that the galaxy's own Lyman-alpha light could then escape through before the wider universe around it had reionized, essentially punching its own hole in the fog well ahead of schedule. The second possibility is more dramatic. Some researchers have raised the idea that this galaxy might be hosting an active galactic nucleus, a supermassive black hole in its core, actively feeding on surrounding material and blasting out enormous amounts of radiation in the process. A black hole like that could produce exactly the kind of intense, localized ionizing radiation needed to clear a bubble around the galaxy, far faster and far earlier than star formation alone could manage. If that's what's happening, it would mean supermassive black holes were already forming and already growing large enough to significantly affect their surroundings only a few 100 million years after the Big Bang. That's dramatically earlier than most models expected such black holes to exist in any meaningful size at all. The third possibility, one that a separate team of researchers proposed after digging into the data, involves the shape of the surrounding cosmic fog itself, rather than anything unusual about the galaxy. Reionization wasn't a smooth, even process happening at exactly the same rate everywhere in the universe simultaneously. It happened in patches, uneven bubbles opening up faster in some regions than others, depending on how many young, radiation-producing galaxies happened to be clustered nearby. It's possible this particular galaxy simply happened to sit inside, or very close to, one of the earliest and most advanced of these ionized bubbles, a fortunate patch of sky where the fog had already begun clearing earlier than the cosmic average, combined with a slight velocity offset in how the galaxy's gas is moving that helped its light slip through a narrow gap before the surrounding hydrogen could reabsorb it. None of these explanations cancel each other out entirely, and researchers studying the data haven't settled on a single answer. Each one, if it turns out to be the correct explanation, tells us something different and significant about how the universe's very first structures actually came together. And that uncertainty is the whole point of why this signal matters so much. It isn't strange because nobody can measure it. It's strange because measuring it perfectly still isn't enough to explain how it got here. Now, try to actually picture the environment this light had to travel through to reach us. Imagine standing inside that early universe, just 330 million years after everything began. There would be no full sky of stars stretching out in every direction the way we see today, just scattered points of intense light, isolated pockets where the first stars and galaxies had begun to ignite, surrounded by a vast, cooling, largely invisible sea of neutral hydrogen gas stretching for unimaginable distances in every direction. That gas wouldn't glow. It wouldn't twinkle. It would simply sit there, an immense light-absorbing haze, swallowing almost anything that tried to pass through it at the wrong wavelength. For a beam of Lyman-alpha light to escape a young galaxy at that moment in history and travel, uninterrupted, across billions of years, all the way to a telescope orbiting a planet that didn't exist yet, something in that immediate environment had to already be unusually clear. A hole in the fog, however it got there, at a moment when the rest of the universe was still supposed to be locked behind it. Here's why astronomers care about this so much beyond simply enjoying a good puzzle. The timeline of reionization isn't just a footnote in cosmology. It's directly tied to how quickly the first stars and galaxies formed, how fast they grew, and how energetic they were while doing it. If galaxies like this one were already producing enough radiation to carve out clear bubbles in the cosmic fog this early, it means the process of galaxy formation in the first few 100 million years after the Big Bang was more efficient and more violent than most existing models accounted for. And if the explanation instead points toward an early, actively feeding supermassive black hole, that reshapes an entirely separate and equally difficult problem in astrophysics. The question of how black holes with millions or billions of times the mass of our Sun managed to grow so large so quickly when the universe had barely had time to assemble its first generation of stars. Researchers aren't finished with this galaxy. Follow-up observations are already planned, aimed at nailing down exactly what's powering that unexpected glow, whether it's unusually hot star formation, an early feeding black hole, a lucky patch of early cleared fog, or some combination of factors nobody has fully modeled yet. Every additional hour of telescope time pointed at this one small, extraordinarily distant object adds another piece to a puzzle that right now genuinely does not have a settled answer. And this isn't an isolated case either. As Webb's surveys continue scanning deeper and deeper into the earliest years of the universe, astronomers have been steadily finding galaxies that appear larger, brighter, and more developed than standard models predicted for their age. This particular Lyman-alpha detection is one of the clearest, sharpest examples of that broader pattern, a universe that appears to have gotten its act together, forming stars, forming structure, and in some cases apparently forming supermassive black holes considerably faster than the standard timeline allowed for. Every one of these discoveries is a small crack in a framework that had otherwise held up remarkably well for decades. And cracks like that are exactly how physics tends to move forward, not through comfortable confirmations of what we already expected, but through stubborn little anomalies that refuse to fit cleanly into the existing picture. So here's what this actually adds up to. A galaxy, seen as it existed only 330 million years after the beginning of everything, is sending us a very specific, very bright kind of light that, according to every serious model of the early universe, should have been completely absorbed before it ever had the chance to leave its own neighborhood. The measurement is solid, the instrument is precise, the result has been published and checked, and astronomers still don't have a single, settled explanation for how it happened. Somewhere in that tiny ancient patch of sky, something burned a hole through the fog of the early universe far ahead of schedule. Whether that was an unusually intense burst of star formation, an early supermassive black hole already feeding on its surroundings, or a lucky pocket of space that cleared out sooner than everywhere else. Right now, nobody can say for certain which one it is. What we do know is that the universe, in its very first few 100 million years, was already doing something more complicated and more energetic than the models gave it credit for. If stories like this one, grounded in real published research instead of exaggerated headlines, are what you want more of, subscribe to Final Proof and turn on notifications. Webb is still scanning deeper into the early universe. Researchers are still chasing an answer for this exact signal, and there's a real chance the next round of data finally explains what's actually happening inside that impossibly distant, impossibly early galaxy. Thanks for watching, and I'll see you in the next one.